So it's been mostly about monads, but before that, chapter 6 also introduces a lot of lenses. So it's like two of these kind of concepts that you find when you learn Haskell. And well, this was both the concepts are introduced there. We have some discussion during these weeks. Maybe if I ever get to write another edition, maybe it's good to introduce maybe lenses a bit earlier, so you don't get everything on one chapter. But unfortunately, that's what I wrote. That's what it's written on the paper. So before diving into the monad things, I wanted to talk a bit. So that, well, this is just my outline, and I have the places where I have to thank you for the help on doing this, and to giving some pointers of what it could be interesting. Yeah. So the first thing I wanted to mention is that, well, the chapter talks about lenses, talks about traversals, and and these lenses, traversals, all of that are actually part of of a framework, sort of a conceptual framework called optics. So there are many kind of optics that people have been doing, have been sort of discovering or found useful. And since I wrote this book, uh, optics have become like better in Haskell. So I wanted to. I think this that now we have libraries which are like ready to use and nicer tutorials. So I would actually like I would actually invite people to look at those. So maybe let me show one. So we have this optics package. So here in Firefox. So this optics is one of the packages. So when I wrote this book, this package didn't exist. Uh, but I found this library to be actually very good, especially for beginners, because it gives you nice error messages. And one of the nice thing it also has is that if you go to the optics, module, it has a great introduction to what every kind of optic is and how you use them, and it has like a lot of diagrams telling you about the relation. So if you want to dive into optics a bit more and you want to know what things are, I would recommend to read this. But also, if you want to use optics, I would recommend maybe do not use the lens package or the micro lens package, which are great, but they are a bit harder to use. Try to use this package, because one of the goals of the author is to make it easier for people to use it, so it gives you better error messages and things like that. Apart from that, there is this, I remember correctly, it's lens tutorial. Yeah, lens tutorial, and that's also a tutorial about well, as it says, what the problems of lens library solves and when it's appropriate to use it and so on. So it also has a lot of information about how lenses are built. And this second tutorial, it's more focused on the implementation. It actually introduces what's called Van Laarhoven lenses. So it's actually a Dutch name. So just somebody from around here was the inventor of this idea of how you can implement lenses in Haskell. So if you're interested in this, you can have a look at this. So I'm just sort of pointing at this materials because, well, I so let's say when I wrote the book, I thought that optics and lenses were useful and they were starting to be used. But as time has passed, actually more people have started to use lenses and other kind of optics, and new libraries have come. So I think that now, even more than before, it's worth learning this. And the concepts are not well, if you mix it with many other things, they are hard, but the concepts underneath the basic optics uh, could be can be learned. So I would just, if you want to go that path, you should just try to get the optics library and work on this. Yes. So that's the first thing I wanted to say about optics. The second thing is a pointer that was made by Yuri about that when you use this kind of libraries, lenses, you often need to, you write your data point, like point, x is an int, or y is an int, and then you have to write something like this, make lenses point. And well, that's actually some template Haskell. That's like the meta programming, the code that write codes for you facility in Haskell. So you have to write something like this, and this make lenses, it what actually generates two lenses, a lens which goes from point to int. Well, actually x and y in this case are both the things, which is great. But of course, that means that you need to call these make lenses, and you need to write the right names x and y with an underscore to get the lenses. There is another package called generic lens, and before telling you what generic, well, no, let me first tell you what generic lens does for you. So generic lens is essentially a way to get lenses in which instead of writing this, you write this weird syntax. So this essentially tells you, please get me the field name x in my object. So whereas, so for example, you can say here, okay, p and then access. So the access operator, if you remember from lenses, is caret dot. So from p access the field x. Yeah, I see a question. I'll answer once I finish with generic lens. So you can use this, and this uses some magic, which at compile time will actually check that x is the name of a field. So even though it's an x between quotes, this is actually checked at compile time. So it will check that the x exists and it accesses the right x for you. So if you would write here set, then you will actually get a compile time error. So this is quite great. And this means that if you don't care writing these kind of things, you can get away without writing these make lenses. And how this works is because it uses something called generics. So when in Haskell we talk about generics, we almost never mean generics in the sense of Java or any of this language, in which generics is what we call parametric polymorphism. So this idea of having like list of A, this is like a generic function. We say it's a polymorphic function. We use generics to mean something else, which is a framework in which you can write code which does some kind of reflection, like reflection in the sense of Java or C#. So it can do reflection over the values you're writing, but this reflection is type safe. So it's actually, I mean, one of I'm in love with this feature of Haskell. So I can write these kind of things, and I could, like, using generics, it actually traverses the type and checks whether there is an X, and otherwise it fails. And this is all done at compile time. So all these checks are done at compile time. So you know that things won't break, as opposed to other forms of reflection where you essentially can just fail and you have to manipulate all these failing cases at runtime and not at compile time. So if you want to know more, I mean, this is something I actually, as I said, I like a lot, so I can give you a bit more pointers. Yeah, a few months ago, I gave like a 4-hour workshop on generic programming in Haskell. So uh, I leave the pointer. If, when you finish the book, you feel like doing some more advanced Haskell, this is a nice thing to know. So while doing this, I got a question. People usually recommend not to use template Haskell. And what's my opinion on what's alternative? So I'm maybe one of the people who are less against template Haskell. To give you an idea of what template Haskell does for you, it's essentially the following thing. So this make lenses, it's nothing else that that a normal function which takes a name, and this name is something defined in the template Haskell library, and gives you back, which is called a declaration. And this queue well, we don't have to go into details, but this queue is called the template Haskell monad, and it's, this kind of thing is monadic because it sometimes need to do things with the compiler. So make lens is just a normal function, and this name and this dec are things built into the compiler which refer to names or declarations in the compiler. So make lenses, at the end of the day, it's going to be some code which it spits out. So it's going to be some function which, instead of spitting out a number, it spits out code. And that's what dec is. And then the compiler is able to take this code which has been produced and sort of paste it there. So that's the idea behind template Haskell. So just as I said, you just write code which produces the code which you end up writing there. And this has a long story. So if you know about macros, this is essentially the same idea, but giving it a bit of type safety. If you've been using Lisp, Scheme, Racket, Clojure, I think Elixir also has macros. So there are many of these things. So the problem and why people don't like it so much is that it's actually quite slow. So if I write make lenses, the compiler needs to execute. So it usually just goes, from top to bottom. It just compiles the entire thing, done. But now it has to go compile the first part. Then it finds some template Haskell code. So you see this looks pretty much like a function call, and it is a function call. It's a function which generates a bunch of declarations. So it has to stop, execute this code somehow apart from the whole mechanism. And then once it's executed, it has to sort of paste it and keep going. And if there are many of those, this actually makes compilation quite slow. Because, well, template Haskell is inherently slow in what it does. So that's the main reason why I think people don't like template Haskell. You can in many cases you can work around this problem. So template Haskell is slow, that's right, but DHC also does kind of good work in avoiding recompilation. So if you can, for example, define all your data types in a single file with all these make lenses calls, and then you never change that one, you only import it, then you will never, this will be compiled once. So that's how you can avoid this problem. For many things, template Haskell is the only thing we have. So for example, if you want to programmatically generate declarations like here, like make lenses does, you have to use template Haskell. There is nothing else which can generate new things for you. The main alternative is actually generics. So the other thing that I'm doing here. And generics allows you to write code which depends on the shape of your data types. And for many cases, this is actually all that you need. So imagine, for example, that you want to write code which generates JSON. So in the olden days, you will have a template Haskell function which will write the code for you. But nowadays, people use generics to write this code. And generics is actually a bit faster, which, okay, you end up with almost the same problems. But the nice thing is that it's more type safe and it's sort of integrated better in the language. So it's not just, a way to have things and then paste them. It's actually something which is integrated as an notion within the language. So that's the main alternative for template Haskell. But myself, I mean, if you see the code I've written, some of the libraries I have used template Haskell extensively, because sometimes it's the only thing you have, and sometimes it's also the best way to generate the best code for you. So something, if you really want to generate code which is fast at runtime, like this, it could be the case that using generic lens is actually slower than make lenses, because make lenses generate exactly the code you need, and field is something which the language has to reason about at runtime. So that's what I wanted to say about lenses and optics. I don't know if there are any other questions about those or template Haskell. In the meanwhile, I'm going to turn the lights on 1 minute. And you can all see I am wearing pants. I'm not like one news reporter, which, these news reporters, which they say they are under underwear. Good. So, the other thing before going into monads is this kind of tricks that you've learned. Many of you may have learned is using debug.trace. So debug.trace is a special function built into the compiler, and it's like the way which we do like console.log or printf debugging in Haskell, which in many cases it's not the only way you have to debug things, but it's quite useful. And the trick goes essentially like this. So whenever you are writing some code and then you want to know what is the value of this thing, or you want to know that you have passed through this part, you just call trace, give it a string, which could be whatever you want. So I don't know, usually people usually do things like, okay, I want to show some kind of tag and the name, and then you write the rest of the code. So I don't know, it could be that f of n is this, and then I write n plus 1, and I'm not pretty sure. Let me see if I can maybe instead open a terminal. Yeah, here I am. So let me open GHCI and import debug.trace, and then I'll define, as I said, well, trace number show n, and then I'll return n plus 1. So if I call f of 3, whenever n plus 1 is going to be executed, this debug.trace prints the code before. So that's a trick. And debug.trace, so the trace in debug.trace is actually, it escapes out of any kind of type safety. So the type of trace, it's like a lie. So it has a string to A. So it's like you give a string and something, and it returns something. And there is a side effect, but you cannot see this in the type system. And that's because this is intended only for, as I said, for debugging. So it will print this, but in theory, it's not doing anything else to your program. And that's, I mean, in many cases, as I said, this is a really good tool to do this kind of debugging, in which you want to know things while the program is running, or you want to know if this branch has been taken. To give you a complete overview, apart from this, GCI has actual debugging powers. So I can write breakpoints. So I can say break on F, sorry. I think I always forget how. Yeah, read C3 is not interpreted. Okay. I don't know what does mean, what that means. Maybe I should try. Well, maybe I should try to load another example3, examples3.hs, and have a module examples3 where, and then write something like f of n equals n+1. And then I'm gonna load this examples3.hs, good, and hopefully I can now write a breakpoint of f. It's not interpreted. Okay. I will look it up for the next session, but I just wanted to mention that there is a command to like make a breakpoint, and then once you get there, you actually get a breakpoint, and you can step through this. You can maybe see from the fact that I don't remember this, how not often this is used. And the reason for this kind of more usual breakpoint debugging not being so used in Haskell is that due to laziness, it's very hard to know what next means. So if you set a breakpoint, you know it's gonna break there, and then you hit the next button, and then you think, okay, I'm gonna go to the to the argument, but it turns out that because this was only needed partially by another function, the next thing which I did is something completely different. So it turns out that okay, you can try to do this. It's built in, but almost nobody uses it. People tend to do debug the trace and somehow get logs of what it's going on when debugging these kind of things. Okay, so that was about debug the trace. And now my next point is history lesson, functor, applicative, monad, and monad fail. So something that you might know until right now is that there are these two important type classes in Haskell. One is the class functor f, which has map a to b to f of a to f of b. Exactly. I'm scared for him now. Oh, here's somebody. Oh, okay. And then there is this monad f where we have the return. So that's essentially this, and f of a to f of b to f. So those are the two main things that we have in Haskell. But if you try to write an instance for monad, you are told something about something called applicative. So I don't want to go into details about what applicative is. There is some discussion in the Discord which you can follow, but I think it's chapter 10 in which I deep dive into this notion. I just wanted to tell you a bit of a history lesson about how Haskell can be changing through the years, so that you know why some of these things are now outdated, or you need some other notions. So it used to be that Haskell 98, that was the first standard, and Haskell 2010, that's the current standard, so it's already 10 years old, define things like this. So this is what monad and functor look like. So functor takes a function and lifts it to f, Then we have monad, which has this return thing, and the bind, and then a fail, which was used when pattern matching failed. So if you don't see very clear where fail fits is when you are doing the following thing. So if remember that if I have some do notation like this, and then I do blah with x, this is essentially translated to something, and then bind, and then lambda x, and then blah of x. So this is the translation. Now it turns out that in Haskell, every time you have the name of a variable, you can also pattern match. So you can do something like this. Now the question is, what should be the translation here? There is one possible translation, that's to write something like this. And this, when you write it, actually is translated again, because when you have a pattern match like this in a function, this actually means that you want the rest of the cases to fail. So this will actually turn into something like case of just x, it's blah x, and any other cases goes into error. That's what you do if you would translate this kind of thing like this. So you can actually try in your, we can try here. I mean, I can just have a function which says g, it's g of just g pattern matches only on just x and returns the x plus 1. And then if I do g of nothing, this will raise an exception. So non-exhaustive patterns in lambda. But the problem is this didn't work that well if you want to see failure as filtering. So if, with the list monad, the notion of failure is filtering. So they came with a different solution. They said, okay, if we have this, we are gonna do what we are gonna do is we're gonna directly do like this. So we're gonna let me copy this. So we're gonna do something like this, but instead of calling error, we're gonna call a special fail function from the monad. So it's like you fail in a different way, and that allows you to control failure within the monad. That was the idea originally. So that's where the failure comes. So it comes from possible pattern matching and the idea that some monads intrinsically have a notion of failure. Like, for example, if you have a maybe monad, you have nothing. If you have a list monad, you have empty list. And this is useful because that means that, or well, it's useful, it's good in the sense that now if you write the following thing, if I write just x something, and then, well, return blah x, this is exactly the same when you have the list monad as doing blah x for just x something. So the creators of Haskell really wanted to keep these two notions together. So in order for this to be exactly like this, you needed to translate through some special failure, because otherwise what you would get be an exception at runtime. So that's why fail was there. Okay, so fast forward some years, and then you come to something which was like a very big discussion, maybe less than 10 years ago, which was called the AMP. That was the applicative monad proposal. That essentially is that turns out that there is a notion in between functor and monad. there is a notion which you sometimes want to talk about, which is called an applicative. And as I said, I don't want to go into what applicatives are, but well, they have these two functions, pure and app. Somebody was saying, okay, how do you pronounce these names? Well, this is app, this is bind. So that's how we often pronounce these names. Yeah, an app has this form. Again, I don't wanna enter into details, but it turns out that every monad is an applicative, and this the hierarchy was turned into this. So you had functor, then applicative, then monad, and that means, if you remember about type classes, that means that every time I need a monad, I need to write an applicative. Every time I have an applicative, I need to write functor. Sorry. So that's where it comes from. So this kind of a split. I still think that conceptually, it's a good idea to explain functors and then monads and then applicatives, even though the hierarchy they are different. I think that's best from an understanding point of view. So that's why it's done in this way. But the trick is that actually, if you have a monad, because it's any of those, you can always write you have one way to define all of those. So imagine you have been able to write your instance monad or your super cool type. Okay, so this instance has some return, some bind, some of everything. So how do I write an applicative? Well, I can always write an applicative by saying, well, my pure is actually return, because it turns out that this return thing is actually not needed, because if it's an applicative, it comes from there, it's the same function. And then you can say that this is equals to app, and app is a predefined function in the library, which has exactly the type you need. And then you can always write the instance of functor super cool t by saying that fmap is something called lift m. So that's that's the trick we often use when you write this thing. You know how to write the monad. Sometimes writing applicative is harder, but you can always get it from there. I would actually suggest you, if you're interested in this kind of things, you can always go to control.monad in the base library. Sorry, I have to show you this. So here is the control.monad, and then if I look about lift m, you can go here and check the source code of this, and you can see, okay, this is actually how you can always write lift m, which is the same type of a fmap, but for monad. And this is the code, and you see that even it tells you a lot about the types and everything. So it's a great way to do this. So that's how things came to be, essentially. And the last part, which has maybe been in GHC only for 1 year, it's that this has been separated. So now you have class monad f, monad fail f, which means that if you have a pattern matching which may fail, you no longer get a monad constraint, you actually get a monad fail, which sometimes changes your type. But that's essentially how these notions relate to each other. And especially, as I said, for monad fail, this is a very recent change. Okay, I don't know if there, yeah. I'll keep talking about monadic things and these kind of things, about monoid and alternative and monad plus and things like this. But please feel free to send any other questions about this kind of monad notions. So it actually turns out that the fail is not the only way you can fail. There is another type class which is for failing stuff, and which actually embodies the notion of failing more. And this class has two names. It's like a bit weird, but again, it makes sense historically. So we have monad plus. The monad plus is an extension of monad, which we have M0 and M plus. Let's look like this. And then we have alternative, which is the same thing, but only extending applicative. So, and those are called empty and I don't have a name for this. I just call it pipe between bars or something like this. And they look they look exactly the same because actually they are, in all practical terms, monad plus is just alternative plus being a monad. So you could imagine having like, like you have applicative and then you have monad and alternative, and then if you join those two, you get monad plus. And this is for things which again might fail, which essentially makes M0 meaning failure, but also when you can try different branches. So both maybe and list have this idea that you can try one thing or another. So that's like what this tells you. So if you can write things like, okay, if I have just 3 or just 5, the result is going to be just 3. So it gets the first thing. If I have nothing or just 5, you will get the just 5. So that's the idea. In the case of maybe, if you have like 3 or 5, 7, this just concatenates the entire thing. So this is when you have notions, I said, where you have failure or nothingness or things like this. So let me have a bit more light. And that's where monad plus comes in. And some people were asking, okay, I have monad plus or alternative. So the as I said, this is not very important. And for all practical terms, people just tend to use alternative, even if they need to use like monad and alternative. That's preferred to monad plus because the names tend to be nicer and easier to read. So if instead of this I write M plus, I need to write something like this to make it similar between back quotes or right in the front. It doesn't read as nice as this, which strongly suggests one thing or the other. Okay, but the question was, okay, what's the difference between having something like this and let me just have alternative and having the class model, where you have it's called memT. It's called memT, and it actually has a thing which looks like this. You can often see this too as mappend, like monoidal append. So the answer to this is, of course, they are clearly very similar, and you can imagine being able to generate a monoid from every alternative thing. That's something you can do. So you could imagine saying, well, if your thing is an alternative, you can write the other thing. But okay, before going so far, let's look at some of these monoids. So the important thing is what we call the kind of this type. So what kind of things could go into M and what kind of thing could go into M here. So if you see, the M here has to be what we call a ground type. It has to be something like int or bool, because it appears alone here. And we write this by saying, well, M must be a type. You can write this in Haskell. So that's called the kind of a type. So when you call, like, kinds are like the types of types. So the kind of M must be a type. It has to be, as I said, a real type. But when we talk about alternative, these M's are applied to A's. So these M's are not types. They are type constructor. They are things which you can apply a type to. So we write it by writing something like this. It has to take a type to another type. So for example, we can say that instance alternative for maybe, because maybe is something which takes a type. So I have maybe, I have to give it a type to create like complete type, that which is maybe int. And I cannot write an instance alternative for bool, because bool is not a type constructor. It doesn't take a type. It doesn't take, so bool of A, which is what you will get by replacing bool here, doesn't make sense. This is just ill kind. We say it's ill kind. It doesn't make sense in the realm of types. And the same happens, so the converse happens for monoid. I cannot write an instance for monoid. I can write an instance for, sorry, just, this is okay. This is wrong, so bad. I can write an instance monoid for bool, that's perfectly okay. I cannot write an instance monoid for maybe, that's gonna be bad. And the reason is that I cannot write the type maybe to maybe to maybe. But what, I guess you hear the baby crying. Yeah, sorry about that. Oh, I got, I got lost. Okay. So yeah. So this is not okay. But what it's a bit confusing for sometimes, that you can actually write this thing. You can say maybe of A is a monoid, and this is different from maybe of A, because this is okay because I can write a function with this type, and I can actually write something for this. I could say that my empty is nothing, and my is the same thing as my pen. And actually I can do this for any. So yeah, let's keep on going with this. So and that's where the difference comes from. So monoid is a notion which applies to a full type, a ground type, and alternative is a notion which applies to this thing. So when you have an alternative, you are saying something is stronger somehow to a monoid. So a monoid, you say, okay, for this specific thing, it's a monoid. But for alternative, you are saying, okay, if you have a list, whatever the elements inside of the list are, I always have a notion of emptiness. And for whatever the notion of whatever the elements of the list are, I have a notion of putting them together. So that's like a stronger notion. And also, well, as I said, in the kind level, they are different. So you cannot use one when you use the other. There is a question in the Q&A saying, will the pipe between brackets always behave the same as M plus? It's more like the converse. So if you have an alternative, then M plus should be like this. There are some weird cases of functions which which don't work the same. And the reason for this is because there is a long discussion about the following fact, about the following law, about the following rule, which things might behave. So if I have something like M0, and then I bind it using a monad with something with some f, there are like two ways that you can get a reasonable answer of this. Some people say, well, maybe the law should be that this always gives me M0. Some other people say, well, it should always give me f. And if you think, for example, what happens with maybe if you have M0, which is a nothing, and then you bind whatever, then it always gives you nothing. So it works like this. But for other monads, it doesn't. So some people say, well, we should actually have two notions. So like this is not really a monad plus, because it's not joining things. It's what they call a monad zero. And you can look for, so if you look for the idea of monad zero in the internet, you will find discussion about this kind of thing. So what is the difference between monad plus and monad zero? So yeah, so for some, but for alternative, usually there is only one way you can implement this. So what happens is that due to some kind of historical artifact, you have a monad plus which implements one idea, like implements something which behaves like this, and then the alternative behaves in the other way, and then they do not coincide. But people usually see this as problematic. People assume that if you have M plus and the OR, you can just freely replace everything by an OR from the alternative. So that's how it should be, but it's not always the case. So that's the other thing. And then the last thing I wanted to mention, and again, thanks to Yuri, who has written a great explanation of this. It's how logic T works, how not logic T in itself, what the notion, because in the book what I talk mostly is about this special version of bind, and I don't want to go into the details of the implementation. As I said, there is a thread in the Discord which you can read, and it's, I think it's really enlightening how it actually works in terms of a even simpler notion called M split. But I just want to give you an idea of what it is about. So imagine, you know, the easiest thing when what you want to do with this kind of logic monad is do something like this. So, imagine I have I have two lists. So this is so like the Cartesian product, and I have, well, of x and y's, it's going to be do take from the x's. I'm actually going to write it in one line by using the special syntax that in Haskell, which allows me to do this, and return x comma y, which it's the same thing if I've written in list comprehension syntax x comma y, where x is x's and y come from y's. So, if there are any questions about, you know, how I wrote this code, feel free to ask. So in theory, Cartesian just works. Yeah, I can just copy it here, and I'm gonna open a new session. I'll just copy it here. That's okay. And then the Cartesian product of 1, 2 times 3, 4, it's going to be all the set of pairs taking one from the other. So you get something like 1, 1, 4, 1, 2, 3, 2, 4. Good. So it's doing what it's would expect us to do. Now, the problem is that in Haskell, this could be infinite. And this gives us in this case. So let me try to take the first 10 elements of the Cartesian product of 1, 2, and then every number from 3 on. You see, it gives me 1, 3, 1, 4, 1, 5, 1, 6, 1, 7. But because this is infinite, I will never get to a tuple of the form 2 something, because I will be indefinitely getting 1 times the other things. So and when you're doing search problems, this is problematic because you are sort of going into a rabbit hole. You're digging deeper and deeper, and you forget to see anywhere else. And this is something which you wanna avoid. So the logic-t package defines a version of bind, because remember, this is also the same thing as access bind y's access bind y's bind return xy. So all these 3 things are exactly the same thing. There's 3 different ways to write this. I mean, I guess Haskell is not a very Pythonic language in the sense that we often get several ways to do the same thing, but I want to show this because it highlights how the solution is done. So what logic-t does is say, okay, what if our bind, so it sort of puts the culprit is the bind thing. It's what it's sort of always going on one thing and then sort of having to finish one entire thing to go back to the previous one. So you have to go all the way back until you backtrack. So what they've done is just say, okay, we're gonna define a new version of bind, which is almost the same, except that is what we call a fair operator. So I don't have logic monad here installed, but what will happen essentially is that instead of doing one thing and then all the steps, is kind of does one thing and backtracks, tries the other thing, backtracks. So if we would take this thing, what we will get if we actually Cartesian in the last form, we will get something of the form like, okay, 1 and 3, and then go, okay, we did one step here, go back and do another step in there, 1 and 4, and then 2 and 4. Of course, the final list is going to be infinite, and it's going to contain the same elements, but the order is different. And when you are searching, and remember in this search problem, all you want to do is to find the solution and then stop. So you will have something which filters here, and then it says, okay, once you found the first one, stop. Then this is important, because if your solution didn't start with a 1, but starts with a 2, then as I said, you have to go into a rabbit hole. So I don't know, imagine a very stupid case. It's gonna be like incredibly stupid, but you want to find the first one in which both elements of the tuple are even. Well, the version with Cartesian is never gonna find it because it always gets a 1 at the beginning. But there is a solution which is just is there. It's gonna be 2, 4. So by making this thing fair, you can you can search the space in an often nicer way. And that's what logic-t does. That's the problem. The problem is that you go into rabbit holes and then you just make bind slightly more, well, not maybe more intelligent, but you try to do things in a different way. Yeah. So you mentioned it looks like logic-t should be even more usable with qualified to find no mistake. It should be usable with do notation then. So some context, qualified do is a new extension they are defining for GHC in which you can override the do notation, and then instead of using the usual bind operator, you can give your own bind operator. And people like this because, well, that allows you to be more explicit, but also to, in a small block of code, override what you would get. And especially when especially for cases which are more advanced, but where what your bind may not have the same type as the usual bind, so it doesn't have M of A to M of B to M of B, but something slightly different. And there are people out there which want to use linear type, which is another extension, or they want to use index monad, which is a more complicated version of monads. They want to do this. So what you could do is say, well, in my logic T, my do notation uses this first thing. There is one thing though. There is a reason why they kept both things. I think the reason for this, well, apart from being able to extend monad and not change all the things, that you actually wanna do this in a clever way. So it's not the case that you always wanna do the breadth first, this more fair version, and then sometimes and never the other thing. You might get into similar problems, maybe a bit more complicated. But what if now the first thing is the thing, and then you define this way, might be, you might get those. Okay. Yeah. Okay. The depth can say, well, maybe I could talk a bit about what's the relationship between monads and effects. And monads transformers and effects. And all about why we need monad transformers. It's like 1 hour long instead of like a 5-10 minute explanation. I'm gonna do this, so I can link to it later. But what's the problem? So idea, because well, essentially they said, okay, whatever it is, whatever effects, I want to say something like, okay, I have some effects. I have a way to produce effects on some value A, and then a way to produce effects from B, and put these two things together. So that's how it's like I have something with effects now and something with effects, which depends on the previous thing. So I want to put these two things together. And this intuitively made sense, because if you think like of a C program or a Java program, you have blocks of code. So you have some block of code, and then you have some other block of code. And what you want to do is to have a way to put together these two blocks of code. So you want to have like a semicolon, which allows us to put these two things together. And that's sort of where the notion of monad comes in. As I said, there are other ways to model this. The notion of monad was by then one of the best contenders to model these things, and one of the key ideas in Haskell was, okay, we think this is the right way to do this, so we're gonna bake it into the language, and have a special notation, do notations to do this. Now, as I said, there were other competing things, and yeah, even in the 1970s, there were people were talking about something called algebraic handlers. So if you look to a library, which an algebraic handler, sometimes people call them handlers or effects. So nowadays it has like many names, but the idea works. So the idea works differently inside of it. But it exposes a very similar interface. So the idea at the end of the day is that you are gonna annotate the things which are effectful in your type system, and then things are gonna work there. Now, why also I think effect libraries have been doing good is that with the newer version of GHC, we actually are able to do a better fine-grained way to talk about effects. And for this, I need to talk about monad transformers a bit. So, okay, the problem of monad transformers. So essentially is, okay, I have two monads, and then I want to create a block of code which does the two of them. And this is actually not as stupid. So I have the state monad, which gives me like some sort of mutable state. And I have the maybe monad, which gives me the possibility of failure. And then I want to do something like find if there is a path in a graph from A to B, which may fail because there might be no path. And the best algorithm we know, the Dijkstra algorithm, needs mutable state. So to implement this algorithm, I need both. But unfortunately, only with monads, you cannot put them together. You cannot smash them together. And the reason why you cannot do this is I said that you can spend a lot of time talking about this, but it's not easy to do this. So people came with different solution called monad transformers, and monad transformer are the idea that you define like a state T monad transformer. So they often look the same thing, but with a T at the end. Then a maybe T monad transformer. And then when you want to put them together, this transformer, you have to think them as like an onion, like wrapping. So you have like a maybe inside, and then a state transformer outside, and then something to the outside, and so on. So you can write a state T of maybe, or also maybe T of a state. These two things, by the way, are slightly different, and understanding why it's different is actually one of the subtlety of using a monad transformer. So I talk about that on the book. But combining these two things are complicated. So people came with this idea of monad transformers, and this is the idea of as I said, putting two monads together. Now, as time goes, people are realizing that controlling the effects, it's nice. So and Haskell essentially has a very big effect thing called IO, which just puts everything together. So so people are saying, well, I actually want to control a bit more what kind of IO, what kind of things I'm doing in my code. So it would be great if I would have a network monad for networking, and a database monad for when I'm using the database, and a console monad for when I'm doing my console. So I can see on my types that this is not, this is not just doing any IO, something which I cannot control, and that's like what people don't like in their code when using types. They want to know what's going on there. They want to see right there in the type, this is using network and console. So they want to have some notion of type, which is network and console, right? So people are, more and more often defining their own monads, and there are many ways, ways to do this. You might have heard about free monads, operational monads, final tackless, a lot of things. You know, I wrote another book about monads called The Book of Monads. So there's a lot to be said there. But people are doing this, and but if you want to implement some, if you want to have a lot of very tiny monads which you want to put together, but it turns out that the way in which you combine them, it's terrible. This doesn't work very well. So people have been looking at the algebraic effects again, and the reason is that it's actually give algebraic effects are better than monads in that they allow you to, they can be combined easily. So you often see, and I think that's how libraries like Polysemy work, that you have something like an F, and then you have a type level list, like a list of things that the compiler understands, in which you indicate which are the effects you want to use. So you have something which has, that uses the network effect and the console effect. You no longer have to define a transformer or whatever. You can just right there say this is using the network and the console effect. That's all. And that's the main benefit of doing this, the ease of in which you can compose the different operations. And if you are writing code in which you really want to control these kind of things, libraries like Polysemy, like F, like Fuse Effect, they all provide you this kind of interface. The cool thing to run the whole thing is that actually F itself, it's a monad. So even though you are combining your effects in a different way, you can still use do notation. So that's like a kind of cool way to run the whole thing. So if you use Polysemy or any of these things, you end up writing code which looks very much like the normal monadic code. You just use do and things like this, except that you don't have to worry about combining monads. You just stack all of them in this list. And that's kind of the, I don't know if that was enough about the relation on why you want this thing. So at the end, you have the notion of monad. F in most things is also a monad, so you can keep the do notation, but the way you combine things is different. One way it's like this transformer thing. The other thing is using composition of handlers. There is actually a way in which you can even go back and define your F monad by using something called a coproduct of functors. If you ever have the chance, there is a great paper. It's an academic paper, but it's very, very well written. It's called Data Types a la carte. So it's Data Types a la carte by Dijkstra, which works here at Utrecht University, in the university here. So it's a great paper. It actually tells you how you can combine monads in a nicer way, and I think this is what led people started this movement of combining monads in a nicer way, which finally led to the revival of the algebraic handlers, the effects notions, which were, sleeping since 1970s. And yeah, I think that's all I have. I don't know if there are more questions about anything. Yeah, I hope the next chapters become. Let's see what's chapter number 8. So chapter number 8 is working on several cores. That's nice. That's yes, about doing real stuff there. So
yes, nice. I wanted to say, if there are no questions, and since nobody has actually reached chapter 8 yet, maybe you can say one or two things about what to expect in chapter 8. And
sure. Yeah.
Because I believe it's also about monads.
Yeah. So once you know monads, now it's time to learn a lot of them. So that the main ones which allow you to do like real stuff. So chapter 8 is about how you do parallelism and concurrency in Haskell. And well, I think that's one of the cool things you can do, which is, I would say, it's hard in other systems. Having like concurrency, which it's always deadlock free and things like that. So that's the software transactional memory does. So the idea is just use a couple of monads, the par monad, which is about parallelism, and the STM monad, which is about having concurrent state, and then build some things on top of this. So build some programs which essentially execute in several threads, and then, well, you can get the result or whatever. And then also, I mean, since we are at it, in chapter 9, you will finally learn how to deal with IO in depth. So that's about the IO monad and how you can use it. So I mean, these two things happen to be some of the. So if you ask me what kind of transformer things I use and all of that, I tend at the end of the day not to use many of those in my actual code. Just the division IO and IO is enough. So maybe the IO monad and the STM monad as a way to control my effects are the most useful. So that's what the next chapters are about.